Study magnetic fields, problems on magnetic potentials, series on electromagnetic field theory, lecture number 2.51. Study magnetic fields are associated with two types of potentials, vector potential and scalar potential. Magnetic vector potential is purely mathematical quantity. It doesn't have any physical meaning, but it has certain applications, particularly in estimating field intensity when source distribution, current distribution is given. Magnetic scalar potential, it is very much similar to electric scalar potential, but it is defined only for current-free regions. In the present session, the focus is on problems and their solutions which are set around magnetic vector potential and magnetic scalar potential. To begin with, we consider a problem. Finding magnetic vector potential at a field point P due to a finite length current carrying conductor. The current is I. The lower end of the conductor is making an angle alpha 1. Upper end is making an angle alpha 2. Also note that point P is at a distance of h from the conductor. To find A, we set this conductor over z-axis of a cylindrical coordinate system, and notice here it is placed, the conductor is adjusted in such a way that the field point is lying over xy plane. Over the conductor we consider a source point at a height of z. The coordinates of this source point are 0, 5, z, and current element here becomes IDL becomes I dz z cap, as conductor is along z-axis. Current is along positive z direction. Let us also suppose that the source point is making an angle alpha at the field point P, whose coordinates are h, phi, 0. With this setup, we consider the basic or fundamental equation connecting vector potential with current. A equal to mu by 4 pi integral I dl by r. Notice, for the present case, R is h secant alpha. This is h, this is r, this is alpha. Z, this is z, z is h tan alpha. So dz becomes h secant square alpha d alpha. Now substituting these quantities in this expression, what you get is A equal to mu naught I by 4 pi integral alpha 1 to alpha 2. These are the limits. With these limits alpha 1 to alpha 2, entire conductor gets covered. H secant square alpha d alpha z cap by h secant alpha. Now integration, the substituting the limits, ultimately we get A equal to mu naught I by 4 pi natural logarithm secant alpha 2 plus tan alpha 2 by secant alpha 1 plus tan alpha 1 z cap Webers per meter. Note, in solving, we assumed the entire system is in free space. Now we consider another problem, infinite straight line current. So certain current distribution infinite in length is given, and you are asked to find out magnetic potential at point P, which is at a distance of, let us say, rho, at a distance of rho from source. Here, as the source itself extends to infinity, potential current integral relation cannot be used. What he is telling is, we used a relation in the previous problem. That relation we cannot use here. But an alternative is available, that is potential field relation. This potential field relation says B equal to del cross A. Earlier one is integral relation, now it is differential relation. From certain aspects of source distribution, it is possible to estimate at least approximately the potential function. For example, from source distribution, one can say A cannot depend, so let us suppose it is lying over z-axis. A cannot depend on z coordinate because source distribution extends to infinity in plus z direction and in minus z direction. Hence, it cannot depend upon z value. It cannot depend upon pi value 2 because symmetry. So it can depend at maximum only on rho. And direction wise, direction of vector potential is by definition direction of current. As current distribution is along z direction, A can only be along z direction. So from various considerations, now A equal to magnitude, which is function of rho, and z cap. Once A is estimated, del cross A can be computed. It is minus dou A by dou rho phi cap. Notice we are doing this problem in cylindrical coordinate system. So del cross A with A equal to A z cap, we will be getting this. But B is known to us. If you don't know, we can find out easily using Ampere's circuit law. It comes out mu naught I by 2 pi rho phi cap. Now equate these two relations, perform integration to get A. So A rho comes out to be minus mu naught I by 2 pi integral 1 by rho d rho. We have to substitute limits. Let us suppose reference point radial distance is rho r and field point radial distance is rho. Then integration and substitution results in A rho, means vector potential at a field point which is at a distance of rho is mu naught I by 2 pi natural logarithm rho r by rho z cap Webers per meter. Notice this potential is relative potential. We consider infinite sheet current. In this case also, source extends to infinity, so potential current integral relation cannot be used. It cannot give you correct result. So we use potential field relation B equal to del cross A. From certain aspects of source distribution, it is possible to estimate. First we do estimation as we did in the previous example, then we try to find out the exact expression. So estimation becomes easy if we consider the current distribution lying over xy plane with current along x direction. Sheet is over xy plane with current along x direction. Now potential direction, vector potential direction is by definition it is the direction of current, therefore direction of potential is x, as current is in x direction. When it comes to its magnitude, it cannot have x component, it cannot x dependence, or it cannot have y dependence, because in x direction as well as in y direction, the sheet is infinite in extent. So it cannot have that component. Maximum, it can depend only on z. So A is, one can estimate A equal to AZ x cap. Now del cross A can be computed. Curl of A can be computed. We are doing this problem in Cartesian system. But del cross A equal to B. B can be found using Ampere's circuit law. For z more than 0, it is minus. For z less than 0, it is plus of mu naught K y cap. K is current density, surface current density. Now dou A by dou Z y cap, this is del cross A, this is B, both can be equated and integration can be performed to get A. So this is the expression, minus half mu naught K Z minus ZR x cap plus half mu naught K Z minus ZR. ZR is Z coordinate of the reference point. Z is Z coordinate of the field point. This long or big expression can be put in a compact form as A equal to minus half mu naught K Zx cap. We consider a solenoid. We try to estimate the potential inside the solenoid as well as outside the solenoid. We assume the radius of the coil, solenoidal coil, is R, capital R. We use a relation known as Ampere's circuit law for vector potential. It reads like this. Closed line integral A dot dl is phi equal to B dot dA, surface integral. First we consider inside. We consider a point inside, let us say somewhere here. At a distance of rho inside from the axis, we consider a point P. Here we want to know vector potential. Before going further, it is required to be reminded that when current is flowing, inside the solenoid field exists and it is uniform. Outside the solenoid, no field exists, so zero field. With this information, let us proceed. A dot dl integral is A. We consider small loop, radius rho, so A 2 pi rho. B dot dA. B inside is given by this formula. One can find out using Ampere's circuit law too. This is B. Area of the loop is pi rho square. From this, A can be found as half mu naught Ni rho phi. So direction of A is phi, azimuthal. Current is flowing in azimuthal direction, therefore naturally A is also azimuthal. Outside. Now we consider a point outside somewhere here. In this case also, let us suppose the point is at a distance of rho. Now we try to, point is outside. Now we try to apply Ampere's law for vector potential. B dot dA. B dot dA is mu naught Ni pi r square. It is not pi rho square. It is pi r square because field is limited to inside region of the solenoid. Field doesn't exist outside. So B dot dA is mu naught Ni pi r square. It is not rho square. It is r square. R is radius of the coil, solenoidal coil. This side what you have is A dot dl, A 2 pi rho. So by equating, we will be getting A mu naught Ni by 2 r square by rho phi cap. This is potential outside. Now we consider a problem on magnetic scalar potential, infinite line current. An infinite line current is there. We are interested in finding scalar potential. Now place it over z-axis, this infinite line current. It is placed in z-axis. Over z-axis, I can be written as I z cap. Now we consider this defining relation, H equal to minus grad Vm. Vm is scalar potential. For infinite straight line current, magnetic field intensity is given by this formula. One can find out easily if we don't have already. Using Ampere's circuital law, one can find out this expression. And grad Vm, this grad Vm can be found like this, minus 1 by rho dou Vm by dou phi cap. Note this expression is resulted when other components are discarded. Why they are discarded? Reason is this is in phi direction. So in the expansion of grad Vm, we consider only phi. We have to consider only phi component. Other components we need not consider. We need not bother. They are irrelevant. So now equating these two, we will be getting I by 2 pi rho equal to minus 1 by rho dou Vm by dou phi. Solving this integration, performing integration, we will be getting Vm equal to I phi r minus phi by 2 pi amperes. Phi r is reference point azimuthal angle, whereas phi is field point azimuthal angle. Note this problem, entire problem is considered in cylindrical system. Now a numerical problem is considered. A very long straight conductor lying along z-axis is carrying a current. Determine the potentials Vm and A at A. A point is given. This point, note, it is in cylindrical system with reference to 205 and B 4 minus 30. This is in Cartesian with reference to 053. Also find Vm when reference points are at 2 amperes. Also find Vm when reference points are at 2 amperes. Solution. A. First we consider A. Vm and A at 4 pi by 6 0 when Vm is 0 at 205. So this is reference. This is actual field point. Vm we have calculated in the previous problem. It is I phi r minus phi by 2 pi. Substitution, simple substitution gives the answer. This potential assumes a reference at 0, but given it is at 2 amperes. Hence, potential of field point 4 pi by 6 0 becomes 0.75 amperes. So this aspect, 2 ampere aspect is solved. A rho, this expression also we computed earlier just now. Substituting rho or rho, we will be getting the answer as 2.08 Z cap microwebers per meter. Infinite line current, same problem. B part, Vm and A at 4 minus 30 when Vm is 0 at 053. The solution process for B is the same as solution process we have undertaken in A. Only difference is here the points are given in Cartesian. We have to convert these points, Cartesian points, into cylindrical first and then substitution. That is the solution. For a given points 053, 4 minus 30, their corresponding coordinate phi has to be found. Phi is pi by 2 and minus 0.643 radians. So Vm is I phi r minus phi by 2 pi. Substitution gives minus 5.28. This potential assumes a reference at 0, but given it is at 2 amperes. Hence, potential of field point becomes minus 3.28 amperes. When it comes to magnetic potential, rho is required. So, rho is 5, rho r is 5. Both the cases, it is same. So substitution results in 0. So A is 0. Magnetic vector potential is 0. Now magnetic scalar potential for infinite sheet current. We assume the sheet current is over xy plane. Current is in y direction. Now H is half K cross n cap. How this expression has come from Ampere's circuit law, one can find within no time H equal to half K cross n cap. N cap is unit vector perpendicular to the sheet. When we apply to the present situation, it becomes a half K x cap. But H equal to minus grad Vm. This is basic defining relation of scalar potential. H is in x direction. If we expand, we get 3 components. So we consider only x component because H is minus grad Vm. H is in x direction. So only x component we consider. This is x component. This is field. Substitution results Vm equal to minus half K xr by x dx. It results in Vm equal to half K xr minus x. xr is x coordinate of the reference point, x is x coordinate of the field point, k is surface current density. This is expression for magnetic scalar potential due to an infinite current sheet. Note, Vm depends only on x coordinate. It doesn't depend upon z coordinate, it doesn't depend upon y. Only on x. We consider a numerical problem. An infinite current sheet lying over xy plane is carrying a current in y direction. K equal to 15 y cap. Determine potentials Vm A at 4 pi by 6 3 B 4 minus 3 4 considering origin as reference. The source distribution is infinite current sheet and we are asked to find out Vm and A at a point. This point is given in cylindrical system. Another point is given in Cartesian system. Solution. In both the cases, reference is origin and hence xr equal to 0. A 4 pi by 6 0. This is cylindrical. The x coordinate corresponding to this point is x equal to rho cos phi. It becomes 3.464 meter. Scalar and vector potentials then can be computed. Scalar potential is half K xr minus x. K is 15. No? So it results in Vm equal to minus 25.98 amperes. A is half mu naught K Zr minus Z y cap. It comes out minus 28.12 y cap. B 4 minus 3 0. X coordinate is 4. So it is simple substitution. Vm comes out as minus 30 amperes. A comes out as minus 37.50 y cap. Note, current is in y direction, A is in y direction. Here also A is in y direction. Direction of A is same as direction of current. Magnetic scalar potential we consider for the case of another source distribution solenoid. Again we consider the defining relation H equal to minus grad Vm. Grad Vm can be expanded in cylindrical system, rho component, phi component, Z component, but H exists only inside the solenoid, outside it is 0. So inside it is in Z direction, Ni Z cap. So Z, where is Z part? This is Z part. So equating these two results in Ni equal to minus dou Vm by dou Z. So ultimately Vm comes out Ni Zr minus Z amperes inside. Now a problem, solenoid. A long solenoid with radius 10 cm is coaxial with Z axis carrying a surface current K 25 cap amperes per meter. Determine scalar potential, vector potential at all points inside solenoid assuming reference at origin. Here reference is origin and hence Zr equal to 0. Given surface current is K equal to Ni phi cap. So 20 phi cap. So Vm is Ni is 20, no? 20, Zr is 0, so Z is Z, therefore we will be getting minus 20 Z A amperes. B. In this case, given that surface current again is 25 cap, hence vector potential is vector potential. A is half mu Ni rho phi cap. Substitution results in 10 mu rho phi cap Webers per meter inside. Another structure source we consider toroid. Here is shown a toroid structure. Magnetic scalar potential. Again, we consider H equal to minus grad Bm. This is grad Bm expansion in cylindrical system. This is H inside. Here also toroid. Inside toroid field exists. It is in azimuthal direction. It is not uniform as it is not uniform inside. Outside, of course, field is 0. So Ni by 2 pi rho. See, you can see it is dependent upon rho. Rho means, see, inside I consider a point. The distance of this point from origin is rho. Okay. So equating 5 parts, 5 components, we will be getting this relation. So dou Vm by dou phi is minus Ni by 2 pi. So Vm integration, performing integration, Vm comes out to be Ni phi r minus phi by 2 pi amperes. Here is a numerical problem based on toroid. Determine magnetic scalar potential within a toroid considering Vm is 0 at rho equal to 40 cm, phi equal to 0.4 radians, Z equal to 3 cm when H, two different H's are given and we are asked to find out magnetic scalar potential. In A, H is in rho direction, in B, H is in phi direction. A, given H is entirely rho direction, in A, as already mentioned, it is in radial direction. H is minus grad Bm, so it becomes 15 by rho cap. H is 15 by rho cap. Grad Bm is minus dou Bm by dou rho cap. By solving this, we get Vm as 15 natural logarithm rho r by rho. Given boundary condition is Vm is 0 at rho r is 0.4 meter. From this, Vm comes out minus 15 natural logarithm rho plus 13.74 amperes. In case of B, given H is entirely in phi direction. So when it is in rho direction, we have to consider rho component of grad Vm. When it is given that H is in phi direction, we have to consider phi component of grad Vm. That component is considered and equated to the field, resulting in 25 by rho equal to minus 1 by rho dou Vm by dou phi. So Vm integration, performing integration results in 25 phi r minus phi amperes. Given boundary condition is Vm is 0 at phi r is 0.4 radians. Okay, substitution results in Vm. These are some of the problems, some of the aspects pertaining to problems set around magnetic potentials I want to discuss for now.